So in the last class, when we started looking at two-dimensional heat conduction, there was some question regarding the individual solutions, isn't it? Individual solutions of, I'll just come back to this. Okay. So the question was this, whether each of these lines corresponds to different values of n. So answer is no. Each of these lines are not corresponding to different values of n. In fact, here if you look at, so for this particular problem, we get infinite number of solutions, infinite number of individual solutions, isn't it? And since this problem is related to a linear homogeneous differential equations, we can represent all these individual solutions as a weighted sum. Okay, linearly this can be added to give a generalized solution. So this, if you look at this particular equation, represents a generalized solution of this differential equation where all individual solutions are added. Okay, and these are not uh, these lines are not corresponding to the individual values of it. In fact, these lines corresponding to a fixed value of temperature. That's why we are calling them as a isotherms. Okay, so these different lines are for different temperatures. All right. Another thing which I wanted to add here is this particular solution we have obtained using this Fourier series, analogy from the Fourier series. Okay, but you can still get the same equation by using the concept of orthogonality. Okay, but that you have to look at. There are large number of articles published on this. In fact, this particular problem is extremely popular. Is extremely popular in the literature. If you look at, you will see all sort of combination of this equation. Okay. Again, if you wanted to solve it, because here it's a infinite summation, isn't it? But you can go up to n equals to 3, 1, 2, 3, and then also you can get a reasonable estimate of t. Okay. All right. We stop here for this conduction, and let's continue with what we have started on heat transfer coefficient. Okay, so let me share the another file. Maybe I'll just share the another file. Okay. So in the last class, we started looking at the concept of heat transfer coefficient. Just to summarize, what we have looked at is whenever there is a fluid, is there any question? Okay, all right. So whenever there is a heat transfer taking place in a fluid, what happens is it rarely remains stagnant. And for conduction, we require a medium to be in a stagnant condition, isn't it? So whenever there is a fluid and if there is a heat transfer taking place, either because of induced turbulence, mechanically induced turbulence, there is a medium is changing because of the mechanical parts like pump, etc., or it can get induced because of the density difference. But in both the cases, you will see that the medium does not remain stagnant. Okay, so in such cases, what happens? In such cases, the convection is the most important phenomenon. Okay. And in order to quantify the convection, what we have to do is actually we have to solve the velocity problem first, and then based on that we have to then solve the heat transfer problem. So this may become a complicated in a real life situation because solving the velocity problem is not easy. It is easy for a simple case like a laminar flow, but in general it is not easy to solve, isn't it? That's what we have seen using this Navier-Stokes equation, isn't it? It becomes mathematically challenging to solve. Correct. So in such cases, what we do is we introduce the concept of this heat transfer coefficient. Okay, what this heat transfer coefficient does, this includes the effect of velocity, it includes the effect of change in viscosity, density, etc., and everything is combined in this particular coefficient H. Okay, And how we calculate this H? We calculate this H using some experimental data. So we generate the experimental data on a given geometry, and that experimental data we represent in the form of empirical correlations. And these empirical correlations then we use for calculating H instead of solving the actual velocity problem. That's how people do it. Okay, correct. So as I said, this H is not a fundamental quantity. This H, which we have defined as a heat transfer coefficient, is not a fundamental quantity, but rather it is a phenomenological coefficient. Okay, and in a real life situation, what we see is the rate of heat transfer is proportional to the temperature difference, and that constitute the basis of this particular equation. That is the basis for this particular equation. So Newton's law of cooling is based on this particular fact that the rate of heat transfer is actually proportional to the change in the temperature. Okay, and the proportionality constant in this case is H. Okay, all right. So up to this we have seen in the last class. Then we started looking at, can we get some physical insights with respect to this heat transfer coefficient? That is what the question we were looking at, isn't it? Can we get some physical insight on this heat transfer coefficient? So whenever there is a solid and over this solid, let's say a fluid is moving, what happens is the velocity of the fluid very near to the solid surface is zero because of the no slip condition, because of no slip condition, isn't it? And as our distance from this solid surface increases, you will see that the velocity of the fluid approaches to the free stream velocity, isn't it? But doesn't matter whether a flow is laminar or a turbulent, you will always see that the layer which is very close to the solid surface, for instance, this is the solid surface, the layer of the fluid which is very close to the solid surface will always remain stagnant, nearly stagnant. Okay, and most of the heat transfer resistance is primarily taking place in this particular small layer. Okay, so for instance, if this solid surface is at a higher temperature, isn't it, than the fluid, then how the heat transfer can take place between the solid surface and the fluid can be quantified by looking at this particular system, isn't it? Okay, so how much heat will be taken away by this fluid from this hot surface, that we can quantify using this film coefficient here. Okay, so what we are assuming that a film very close to this hot surface will remain stagnant, and when we are saying that this film remains stagnant, that means we can apply a Fourier's law of heat conduction, isn't it? So yeah, as you can see that the the actual temperature profile is varying like this, but most of the change in the temperature takes place only in this film. Okay, so we can assume that instead of taking this entire change over this complete length up to this, we are assuming that the change in the temperature taking place only in this film. That's the assumption. That's the assumption. Okay, this is something called as a film theory. Probably you will also get to know more detail about this when you will look at mass transfer. I don't know whether you have done mass transfer. Have you? Are you doing a mass transfer in this semester? Hello?
No, sir, but we have studied mass transfer to a little in the transport phenomena course.
In the transport phenomena. Okay, so have you gone through film theory there? No.
I think no, sir. I don't.
Okay,
do not.
so in mass transfer, you will get to know more about the film theory. Okay, so the same thing which I am discussing, that we are going to look at in more detail. Okay, so there are different theories. Film theory is there, then there is a surface renewal theory. All those things you are get to know in mass transfer when you will look at diffuser. Okay, all right. So what I'm trying to say is most of this resistance is taking place over this entire length up to this. But we are assuming that since this is the dominant part, we are assuming that it's a realistic assumption that all this temperature difference is taking place only in this small film. Isn't it? Can you see why we are making this assumption? Isn't it? Of course, there is some change here towards the end, but we are neglecting that because that small change with respect to this entire change we are looking at, isn't it? All right. So it's a realistic assumption that most of the temperature change is taking place only in this film. If we are assuming that this is what is happening, then we can apply a Fourier's law of heat conduction here, isn't it? And Fourier's law of heat conduction gives the rate of heat transfer Q is given as minus Ka delta T. What will be the delta T? Ts minus T naught, where T naught is the bulk temperature, Ts is the surface temperature, divided by delta. Delta is the film thickness. And if you rearrange this equation, what we will get is K divided by delta A into Ts minus T naught, and K divided by delta we can represent as H. So this is also one of the derivation of the Newton's law of cooling, isn't it? This is what we have derived, this Newton's law of cooling we have derived from Fourier's law of heat conduction. Can you see? Isn't it? Does it make sense to everyone?
Yes, sir.
So again, in this case, this H is given as K by delta. But this delta, calculating the value of this delta is not easy. As I said, this delta will have, impact of several things. If you increase this free stream velocity here, this delta will further decrease, isn't it? If you reduce the viscosity, then this delta will further decrease, isn't it? It also depends on density, correct? So this delta value depends not only on the velocity, but also on viscosity, density, etc. Isn't it? And all these effect is included in this delta. And that's why I'm saying this H, heat transfer coefficient, is dependent on not only on the velocity, but also density and viscosity. Do you all agree? Hello?
Yes, sir.
Of course, we will solve. Okay. So you might say this, that, we are looking at a very simplified case. Why not solve the entire problem from the first principle without making this assumption of this H, isn't it? Correct? Yes or no? We will look at such problem later on when we will look at the natural selection, natural convection, sorry. In the natural convection, we will see the derivation of one simple problem where we are looking at the laminar flow. So only for laminar flow we can derive. Remember the Navier-Stokes equation we can simplify for a laminar flow, isn't it? Right. So for only a simple case of pipe flow with a laminar flow condition, we will derive the entire heat transfer equation again when we will look at natural convection. Okay, but for a time being, let's do our analysis based on only this heat transfer coefficient. Okay, is it clear to everyone? And as I said that we can solve this entire thing from the first principle only for a very simple cases, not for a the real life complex cases. And that is why this concept of heat transfer coefficient is assumed. All right. Does it make sense? At least the background why we are studying this heat transfer coefficient?
Yes, sir.
Is there any question so far? Hello? Is there any question so far? All right. If there is no question, let's move to a simple problem. So in this problem, what is been given is an ice ball of initial diameter of 0.06 meter is suspended in a room of 30 degrees Celsius. The ice melts by absorbing the heat from the ambient. The surface heat transfer coefficient being 11.4 watt per meter square degree Celsius. So you can see that the unit of heat transfer coefficient is what? It's a unit of thermal conductivity divided by meter, isn't it? The thermal conductivity divided by delta. So you can derive the unit of the heat transfer coefficient, which is nothing but this watt per meter square degree Celsius. In fact, if you look at the unit of thermal conductivity is watt per meter degree Celsius, isn't it? Is it clear to everyone? So the air in the room is essentially dry. If the shape of the ball remains unchanged, calculate the time required for reduction in its volume by 40%. The density of the ice is 929 kg per meter cube and its latent heat of fusion is 3.35 into 10 raised to the power 5 joule per kg. So this is an unsteady state heat transfer problem, but what we are looking at here is the heat is transferred from the ambient to the ice ball, and that leads to the melting of the ice ball, and because of that the size of the ice ball is going to decrease, isn't it? Now the question here is how much time we will require in order to reduce the ice ball from 0.06 meter to its new volume, which is lower by a 50%. Okay, so that's what we are saying, the reduction in its volume by 50%. Okay. In this case, let's assume that the radius is r, m is the mass of the ice ball at any time t, rho is the density, lambda is the latent heat of fusion. So in this case, the mass of the ice ball will be given by what? Mass of the ice ball will be volume into density, isn't it? So volume in this case, volume of this spherical ice ball will be given by 4/3 pi r cube into density will give you a mass, isn't it? Correct. And what will be, and what is happening here, this ice ball is changing, so that means dm by dt is what we are interested in, isn't it? Dm by dt is what we are going to calculate, because how much is the mass of this ice ball is changing with respect to time, that we can directly get by differentiating this equation with respect to t. Okay, so minus d by dt 4/3 pi r cube rho will be the rate of melting, isn't it? Correct, isn't it? So all other factors are constant here, only the radius is going to change. So we can take this minus sign here and we will have 4 pi r square rho dr by dt after differentiating this r cube, isn't it? And again negative sign is there because as time increases, the size of this ice ball is going to decrease, isn't it? Correct?
Yes, sir.
Now rate of melting is there, and rate of melting multiplied by latent heat of vaporization will give you how much change in the energy is there, isn't it? If you multiply, because here we are saying that the ice ball is melting, isn't it? So latent heat of vaporization, if I multiply here, that is going to give me how much is the rate of change of energy, isn't it? So that can be obtained directly by this, isn't it? So rate of heat absorption by ice ball for melting will be 4 pi r square rho dr by dt into lambda, where lambda is nothing but the latent heat of fusion. Correct? And this should be equals to the amount of heat transferred by convection, isn't it? So the rate of heat transfer from the ambient using convection will be 4 pi r square, that is the area of the sphere, into heat transfer coefficient h into delta t. So this is this equation we are directly getting from the Newton's law of cooling, and both these factors should be equal, isn't it? Do you all agree? Yes or no?
Yes, sir.
So we can write down this equation like this, isn't it? So 4 pi r square rho dr by dt lambda will be given as 4 pi r square h T0 minus TB, and we are keeping this temperature same, isn't it? Because ice ball will, there will not be decrease in the temperature of ice ball, isn't it? So this is a slightly different problem compared to what we were looking at earlier. So earlier we were looking at the surface temperature of the ball was changing, isn't it, with time. Here the surface temperature is not changing because of the heat absorbed. The size of the ice ball is decreasing. So that's why this T0 minus TB both are kept as it is, isn't it? So T0 is the ambient temperature, TB is the temperature of the ball, which will be in this case ice we are using, so that will be 0 degrees Celsius. Correct?
Excuse me, sir.
Please go ahead.
Sir, the ice is melting, so its temperature won't change, but the room temperature can change
So
because
room is, we are assuming that room is a very large room, and because of that the change in the temperature of the room is not significant, it's negligible.
okay, okay, sir.
All right, that's why uh, we have said a room, not a small chamber. Okay. Okay. Also, we are assuming that even though the melting of the ice is taking place, but uh, the air inside the room remains dry. That's what we are assuming. Okay. So even though the melting is there, but it is not affecting the humidity in the room. Okay.
Sir, here in this, like the ice will melt and water will form on the surface, तो फिर वो water का भी तो conduction आएगा.
Yes, you are absolutely true, but that case we are not looking at. We are saying that uh, whatever the melting is taking place, that is completely removed. It is not there, but you are absolutely true. In fact, one of such case we will look at later on when we will look at condensation. But you are absolutely true. We will look at such case when we will look at condensation. Yes. Thank you. All right. Good. You are picking up things. All right. So this is a very simplified case in the sense that the whatever is the melting is taking place, that water is completely removed and only the ice surface is subjected to the dry air. OK, and the liquid is not subjected to the dry air and there is no liquid film around the ice. OK, there is no liquid film around the ice. Another thing is we are assuming that the room is very large, so the temperature of the room is not changing. So ambient temperature is still at 30 degrees Celsius. All right. Is it clear to everyone? Hello?
Sir, I have a doubt that in the heat balance expression, in the left hand side, we have the R, that is the new R, right? When the volume is reduced.
So right hand side is also having R.
Sir, but right hand side, shouldn't we integrate the expression to get Q? Because R is varying from initial R to final R.
That is in the Fourier's law of heat conduction, not in the Newton's law of cooling.
So in Newton's law of cooling, we take R as the final R.
HA is there. Na?
Sir, but area is
what
varying.
This A is going to be? What this A is going to be? This A is going to be the this A is going to be the area, isn't it? Area of the ball at that time, isn't it? Correct. And what you are saying is we have to integrate. Yes, but that is what we are going to do it here. This is in terms of R now. We will integrate it, isn't it? This is for any R, isn't it? This is we are dealing in terms of differential equation, isn't it?
Okay.
So we are going to integrate over the R, isn't it? Yes or no?
Yes, sir.
So this dt I can take it on the right hand side and we will have a dr here. So dr I am going to integrate over R0 to, let's say, Ri, isn't it? Initially I had R0 and over the time it is going to change to R. So I am anyway integrating this area. Does it make sense? So this is only a balance, initial balance, isn't it? Yes or no? This is the only initial balance we are using. What is the question? Is it clear or not clear?
Yes, sir, clear.
Okay, so then we will integrate it. We will integrate it. So after integration, this is what we are going to get it. So after integration, we will get R will be equals to C1 minus H delta T divided by rho lambda T. And after rearranging or after putting all the values, remember this ice temperature we have used 0, ambient temperature we already know, H value we already know, the density of the ice is already given 929, and this latent heat of fusion is also given. So that is put here. So by putting everything, what we get is the generalized equation R is given as C1 minus 1.1 into 10 raised to power minus 6t, where C1 is the integration constant. Isn't it? Now this equation, see, for different value of R, isn't it? I will get different t, isn't it? So initially I can apply now a boundary condition here when R equals to R naught at t equals to 0, isn't it? That is what the boundary condition I will have. Do you all agree?
Yes, sir.
So we are putting a boundary condition here at t equals to 0, R equals to R naught, and R naught is what? What is the initial diameter? Initial radius 0.03 meter, isn't it? That is the initial radius. So if I put it here in this equation, what we get is C1 equals to 0.03. So we get a generalized equation. R is given as 0.03 minus 1.1 into 10 raised to power 6t. So this is a generalized equation. How my radius is going to change with respect to time. Now what is been asked in the question? In the question it is asked that to find out the time when my when there is a 40% reduction in the volume, isn't it? That means the current volume of the ice ball is what? 60%, isn't it? So we can find out what will be the radius, isn't it? So if the volume is reduced by 40% of the original volume, we can find out the new radius. So 4/3 pi r cube, this is the new radius, will be given as 0.6 into 4/3 pi, and this initial radius, isn't it? So this is the initial volume multiplied by 0.6, that is the new volume we are going to have, isn't it? After 40% reduction. So we can find out the new value of the radius. So new value of the radius is 0.0253 meter. Do you all able to see what I'm doing?
Yes, sir.
And this R, we can put it here now. We can put this R here in this equation and we can find out time. So that's what we have done. We have put this R here and we have calculated the time. So T comes out to be 4267 seconds. Is it clear what we have done? Hello?
Yes, sir.
So only one thing you will have to notice here is, unlike the previous cases, in the previous cases, this temperature was varying. This temperature of the ball was varying, isn't it? When we were looking at the metal ball, in the metal ball, there is no reduction in the size, but instead of that, the surface temperature of the metal ball decreases. Yes or no? Correct. That's what we have seen unsteady state analysis using the lumped parameter, isn't it? If a metal ball put into a fluid with a different temperature, how with time, how the temperature of the ball is going to change. Correct. So that problem and this problem is nearly the same, except that in that problem, the temperature of the ball, surface temperature of the ball was changing. Here, instead of changing in the surface temperature, the size of the ball is decreasing. Do you all agree?
Sir?
Yes, sir.
Please go ahead.
Sir, in this question, are we assuming that all the heat which is being absorbed is going into the phase transition, right?
Yes,
like
yes,
no heat is going in.
No heat is going in a, there is no sensible heat.
Yes,
there is no decrease in the temperature taking place as per the ice ball is concerned. So that's what happens, isn't it? When the ice is melting, does the temperature changes? Does the temperature changes?
No, sir.
No,
Phase
sir.
transition occurs at constant temperature.
At constant temperature, correct. All right. Can we move ahead?
Yes, sir.
Clear to everyone? Okay, so now let's look at a very interesting case, and this is the most commonly seen case in the process application. Most commonly, you look at any heat transfer equipment, this is what happens mostly, isn't it? So the case, in this case, what we are looking at, so there is a fluid surrounded by a metal wall, and also, so see, whenever we are looking at the heat exchangers like double pipe heat exchanger or in a normal shell and tube heat exchanger, what happens is there is a pipe, isn't it? And around that pipe there is another pipe. So in the annular region, one hot or a cold fluid is moving, and inside the pipe also another fluid is moving. So that means both the fluids are separated by a metal wall. And this type of situation you regularly see. This type of situation also you see in a boiler, isn't it? So there is a furnace. Inside the furnace, there is a gaseous flue gases are there, and then there is a wall of the boiler, isn't it? And outside you will have again the ambient air, isn't it? So this type of situation you will regularly see in a heat transfer applications, isn't it? Where a metal or any other wall is separated by two fluids. Is it clear? At least the situation is clear to everyone what I'm trying to say?
Yes, sir.
Okay. So heat transfer from one fluid to another separated by an intervening solid wall is of a great practical importance, isn't it? And there are numerous examples. I have given you two examples. One example is for the boiler, another boiler furnace, and another example could be for a double pipe heat exchanger or a shell and tube heat exchanger. We will see both these cases in much more detail later on. So in all such cases, you will see that the fluids at different temperatures are separated by a metal wall. So how to quantify heat transfer in such cases? That is the question. So whenever we are looking at the fluid, the convection is the most important part. So in this case, see here, you can see there is a warmer fluid, here is a colder fluid, and in between there is a solid wall is there, isn't it? Now for a warmer fluid, the convection will be there. Again, in a colder fluid, there will be a convection will be there. But inside this wall, there will be a conduction will be there, isn't it? Correct. So these are the cases in which conduction and convection both are present in a series. Do you all agree with me? Do you all agree with me?
Yes, sir.
So there
Yes,
is,
sir.
see, in this fluid region, we will have a convection. Also in this another fluid region, we will have a convection, but in this solid wall, we will have a conduction, isn't it? So in this case, you can see that the warmer fluid is at a temperature T1, isn't it? And this colder fluid is at a temperature T2 here. This is the temperature T2. Now the convection is taking place between this warmer fluid and this solid wall. So the surface temperature on this left hand side wall surface is TW1, whereas the again the convection takes place this hot wall and the colder fluid, and therefore the surface temperature on the right hand side surface of this wall is TW2. So here the temperature is TW. Okay. So let's do the analysis of the heat transfer here. Again, we are looking at the steady state heat transfer. That's why we are getting a straight line here without any curve, isn't it? And there is no generation occurring here in the warmer fluid wall as well as in the colder fluid. That's why we are getting a straight lines here. Do you all agree? Isn't it? Yes or no?
Yes, sir.
So if you would have had here a unsteady state heat transfer, then instead of having a straight line here, we would have had a curved lines which is downward like this. Concave lines would have been there, isn't it? If this would have been the unsteady state heat transfer. Similarly here. Make sense? Isn't it? But we are assuming that the steady state heat transfer is taking place here. And therefore we are having no, so you can see there is a linear gradient is there. Linear gradient is there. Okay. Again, since we are looking at steady state, means whatever the heat transfer through this warmer fluid will be the same as heat transfer through this wall and as well as this colder fluid, isn't it? Yes or no? Hello?
Yes,
Yes,
sir.
sir.
So this Q1 is equals to QW is equals to Q2, and these are all are equals to just Q. Isn't it capital Q? And I can calculate now the individual Q1, QW, Q2, etc. Isn't it? So in this case, let's look at this warmer fluid. So warmer fluid, what will be the heat transfer given by? Heat transfer will be given by Newton's law of cooling. So Newton's law of cooling is given by what? HA delta T, isn't it? What is H here? H1, because we are looking at the first fluid here. So H1 area, cross-sectional area is same here, isn't it? So A, HA, H1A, and what will be delta T? T1 minus TW1. Do you all agree?
Yes, sir.
So that's
Yes.
what is Q here in this first fluid. We can rearrange and we can find out this temperature difference as T1 minus TW1 is given as Q divided by H1A, isn't it? Now similarly, we can look at the heat transfer through this wall. So heat transfer through this wall will be given by Q is given as KWA into TW1 minus TW2 divided by S. So this is the standard Fourier's law of heat conduction, isn't it? Thermal conductivity multiplied by area divided by temperature gradient, isn't it? Whatever is the length of this wall. Do you all agree? That's why we have put KW. Do you all agree with me?
Yes, sir.
So this is coming from the Fourier's law of heat conduction, because only the conduction is going to take place through this wall. We can rearrange this equation and we can obtain TW1 minus TW2 as Q divided by A in the bracket KW by L, isn't it? Do you all agree? We can rearrange, we can take this entire thing on the left hand side here, and KWA by L we can take it on the left hand side. So Q divided by KW by L will be there, and that should be equal to TW1 minus TW2. Similarly, now let's look at this second fluid here. So second fluid, again the heat transfer is going to take place by convection. So Q is given by H2A, this TW2 minus T2, isn't it? And we can rearrange this entire thing. What we will get is TW2 minus T2 is given as Q divided by H2 by A. Do you all agree? All three equations?
Yes, sir.
Yes, sir.
Now one more thing you have to note down here, in both warmer fluid as in the as well as in the colder fluid, we have assumed a film. See here we have assumed a film. Okay, so this is the warmer fluid film, this is a colder fluid film. So there could be a bulk here beyond this or here, isn't it? But as we are saying that whenever the convection is taking place, most of the resistance will be present only in the thin film which is near the wall of the which is near the solid wall, isn't it? So that's why we are looking at this warmer fluid film and colder fluid film here. Is it clear to everyone? Yes or no?
Yes, sir.
Okay, all right. Now we can add all the temperature differences, and after adding the temperature differences, the total temperature difference between the cold and warmer fluid. Remember, T1 is the bulk temperature of the warmer fluid. T2 is the bulk temperature of the colder fluid. Ultimately, we are interested in, see, very often we only know the bulk temperature of the warmer fluid and the colder fluid, isn't it? Correct. So now we are representing this entire equation in terms of the bulk temperature of the warmer fluid and bulk temperature of the colder fluid, isn't it? Yes or no? We are not finding our equation in terms of TW1 or TW2. These are the surface temperature. This will not be known. This will not be known. Are you going to calculate the surface temperature here? Very often we calculate only the bulk temperature, isn't it? Not the surface temperature here, isn't it? Correct. That's why we have added all these temperature differences and we got rid of this interfacial, surface temperatures, intermediate surface temperatures. Do you all agree? Does it make sense what we are doing?
Yes, sir.
You said yes, but that confidence was lacking. So is it clear or not clear?
Yes, sir.
Clear, sir. Clear.
Okay. So unless you guys say it, strongly, I will not feel that, you got it or not. All right. Okay. So please stop me if something is not clear. You ask me 10 times. I will explain it 100 times. It's not problem. Okay. No problem at all. but I want all of you to understand heat transfer by hook or crook. Okay. All right. So I have only limited choices in this online thing, but whatever we can do in online, I will try to explain it again and again. Okay, all right. Most of the time, in a offline classes, I get to know just by looking at you whether you all are able to understand the concept or not, isn't it? But that choice I'm not getting in the online class. In an offline class, I usually just by looking at the student itself, I can find out whether they are getting it or not. So you will have to tell me upfront if something is not clear. Can we move ahead?
Sir,
Please go ahead.
so we are supposed to take the temperatures of the film, but I mean the film size is not known till now. No?
Film size is not. Film size. So where we are taking the film size here? Do you have anywhere we are having a film size?
No,
We are
sir,
having
that-
the heat transfer coefficients. Right. And heat transfer coefficient we can calculate using empirical correlations.
So how will we find T1 and T2 then? I mean, for that we should know how.
T1 and T2 is the bulk temperature.
Sir, do
I can
we
go back. Just
expect?
a bit. Remember here this T0 is already known. This is a bulk temperature. Whatever the temperature of the fluid you are having, that is the bulk temperature, isn't it?
Yes.
Okay, so that is known. So T1 and T2 is known because it's a bulk temperature. Yes, some more question was there in between. Yes, please go ahead.
Sir, do we assume that the bulk temperature of the fluid will be equal to the surface temperature of the warmer fluid or the colder fluid? Basically, we assume that only, right?
Where is the surface temperature of the warmer fluid? This is a fictitious film. This is a fictitious film. It's
so
not the
T1 to be bulk temperature only, right?
We are looking at only T1 is the bulk temperature, and
Okay.
here this surface temperature is TW1, TW2.
Yes.
So T1 and T2 is a bulk temperature. Bulk temperature in the sense is what? Whenever something is flowing through a pipe, you just measure the temperature of that fluid. Okay. You don't look at the distribution of the temperature across the cross section of the pipe. Does it make sense what I'm saying?
Yes, sir. But what I
It's
meant
an
was,
average temperature. You can say that it's an average temperature over the entire cross section.
okay, sir, that's what I was asking, that the temperature profile would be changing, right? So how do we consider this T1? Okay, that would be the average. Yes,
That's the average temperature. That's what there is another name also, which is called as a cup mixing temperature. We will look at this terminology later when we will look at natural convection. Okay. So all these things we are going to at least try to look at for a simple case of laminar flow. As I said that solving this problem exactly for a real life turbulent flow is not easy. It's not at all possible. Okay. But at least for a laminar case, we will try to derive.
Sir, I had a doubt. Sir, if the wall is not there, is it possible H1 and H2 would be different?
If the wall is not there, this wall is not there.
Yeah, so H1 and H2 would be different because.
So if this wall is not there, then you are mixing both the fluids, isn't it? Then it's not a heat transfer.
But instead of this wall, the KW, another conductivity, there is another conductivity of another material. If the another material is there, then is it possible H1 and H2 may change for that?
No, H1 and H1 and H2 is not dependent on the thermal conductivity of the wall. H1 and H2 dependent. Okay, I got your point. So here, okay, I'll again go back to here. This K is what? This K is not a thermal conductivity of solid. This K is the thermal conductivity of the liquid.
Yes, sir. Yes, sir. But sir, delta can change now because it depends on velocity, density.
Delta can change with respect to the velocity, density, and viscosity of what?
Of the fluid.
Fluid
Element.
Fluid, not the solid. So even if you change this solid by, if you change this solid by different solid, the effect of temperature will be there. And because of that, some changes will be there, but not directly. You get it?
It will not be a. Yes, sir. Got it.
So here this heat transfer coefficient, you are saying that that will be dependent on the velocity, viscosity, and density and thermal conductivity of the fluid, and not on the wall. So if you change this wall by some other element, what changes you are going to look at is this TW1 and this TW2 is going to change, because these gradients are going to change, but not the heat transfer coefficients. Heat transfer coefficient will not be changing unless you are changing the parameters with respect to the fluid. That means you are changing a different fluid here. Other than that, these heat transfer coefficients are not going to change. Does it make sense?
Yes, sir. Yes. Thank you.
Okay. So see, if you say that I wanted to change the density, that means you are going to change, or viscosity. That means what? You are going to change the fluid itself sometimes, isn't it? Yes, or no?
Sir. Yes, sir. Yes.
Okay. All right. So is there any question, or is it clear to everyone? Please stop me. Please stop me. Let's make it interactive. Whenever you have any doubt, please ask me. Doesn't matter. See, at max, what will happen? At max, what will happen? If I know the answer, then I will, try to give you immediately. If I don't know, then I will try to find out later. But you need to ask me as many questions as possible. Okay. Then only you will understand many things. All right. And that also keeps me on edge. So I will also go through this material a little bit in more detail. So that helps in both ways. Okay. All right. So by adding all these temperature differences, these individual temperature differences we have obtained, and as I said that this TW1 and TW2 is unknown, we will not be able to find out. Only the bulk temperature we can know easily. So we can add all these temperature differences. So by adding all these temperature differences, what we are going to get is Q by A in the bracket. All these terms will be there, 1 by H1 plus 1 upon KW by L plus 1 by H2. And this entire bracket term is represented as 1 by U. So 1 by U is called as, this U is nothing but overall heat transfer coefficient. Okay. So this is a very important concept. So Q is now given by UA delta T, where U is nothing but what? 1 upon this entire bracket, 1 by H1 plus 1 upon KW by L, 1 upon H2. Here this first factor represents the resistance of the outer fluid, the second factor represents the resistance of the wall, and this third factor represents the resistance of the inner fluid. But the concept of U is used here, capital U is used here. So whenever we have a combined convection and conduction, or even radiation, sometimes even radiation is also represented in terms of the overall heat transfer coefficient, that we will see later. Okay. So whenever we have combination of conduction and convection, this Newton's law of cooling we don't apply directly between the bulk fluid temperature and the colder fluid. So, but rather than doing that, what we do is, instead of doing that, what we do is UA delta T we use, where U incorporates the effect of this film here outside, and as well as this conduction resistance. So all three resistances are included directly in this U, and therefore we are writing this Q, capital Q is UA delta T. This is similar to the Newton's law of cooling. The only difference here is this U is now including the resistances of all three things, isn't it? So first is the resistance, convective resistance in the warmer fluid film, then the conductive resistance at the wall, and again the convective resistance at the colder fluid. All three resistances are included directly in this U, and that's why this U is called as overall heat transfer coefficient. Okay. Is it clear to everyone? Yes or no?
Yes, sir.
So this is what this equation you have to use whenever there is a mixed conduction and convection, not otherwise. For instance, if I am having only a convection, I am looking at this surface and here. Do I require to use this capital U?
No, sir.
I only need to use H, small h. Okay. So this is a small difference. Very often we miss this point. So keep it in mind. We use a overall heat transfer coefficient concept whenever we have a mixed conduction, convection, etc. Isn't it? So here this convective resistance is there, this conductive resistance, and this again convective resistance is there. So everything is coupled here in terms of U. Okay. Another interesting thing to look at is now this equation is assuming the resistance of wall, resistance of the inner fluid, resistance of the outer fluid. But very often what happens? Remember, as I said that if you are using a metal wall in between, let's say instead of this a brick wall or something, let's say this is a metal wall. Metals generally have a very high conductivity, isn't it? Correct? Yes or no?
Yes, sir.
So that means the resistance offered by this metal wall will be what? Very less compared to the resistance which is present in this outer warmer fluid film and this inner colder fluid film, isn't it? So resistance offered by these two fluid films will be much higher compared to the resistance offered by this metal wall, because the thermal conductivity of the fluid will be at least 1 or 2 order magnitude lower than the metals, isn't it? That means the resistance, remember here, even though we are looking at this H, but H is what? K by delta. So that means it depends on the thermal conductivity. So thermal conductivity of the fluid is much lower compared to the thermal conductivity of the metal wall. So that means the resistance offered by these fluid films is very often is much higher compared to the resistance offered by this metal wall. Do you all agree? Yes or no? Does it make sense?
Yes, sir.
Yes, sir.
That means what, this second resistance, which is resistance by wall, we can neglect in some cases whenever we are using a metal wall. So that means this 1 by U can be approximated as 1 by H1 plus 1 by H2. Yes or no?
Yes, sir.
Another simplification is, let's say this warmer fluid is, let's say, a gas. It's a gaseous medium here, and colder fluid is, let's say, liquid. Now remember, the gases will have at least 1 or 2 order of magnitude lower conductivity compared to the liquid, isn't it? Yes or no?
Yes, sir.
So that means what? Most of the resistance will be offered by this gas film outside this wall here, instead of a liquid film which is there. Cases, even the resistance by this colder, in such cases the resistance offered by a liquid film can also be neglected if there is a gaseous film is contributing more, isn't it? So we may even have 1 by U is equals to just 1 by H1, even for a simplified cases. Do you all agree?
Yes, sir.
Yes, sir.
So that is what is written here. In the above equation, sometimes one of the resistance is dominating. For example, metal wall separating the film in the fluid, then its resistance can be neglected. Suppose the heat is transferred from the gas to metal wall and then to liquid. In such cases, the resistance of the gas phase is the most dominating, as thermal conductivity of the gas is lower than liquid and even lower than solid. Okay, all right. Let's look at one of the, one of the interesting example here. This is the double pipe heat exchanger, which I was saying earlier. So this is the inner pipe is there. Outside this inner pipe, there is a outside pipe is there, isn't it? So one fluid is flowing through this inner pipe, which is shown by this shaded area, and another fluid is flowing through this annular space outside here. So both these fluid which is flowing through annular space and the fluid which is flowing through inside pipe, which is separated by this metal wall in between. Can you see? Is it clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
So one fluid is entering in an annular space. It is coming out from this annular space like this. Another fluid is entering through this inside pipe and coming out through this inside pipe. And both these fluids are separated by a metal wall, which is shown by a red lines here. If you look at the cross section is like this. Okay. Is it clear? This is something called as a double pipe heat exchanger. Double pipe heat exchanger. Okay. The well-known simple practical device for heat transfer. It consists of two concentric pipes properly fitted or welded with arrangement for pumping one of the fluid through the inner pipe and the other through the annular space. The fluids are thus brought in thermal contact in order to achieve the heat transfer. Shell and tube heat exchanger is the generalized version of this. We will see when the multiple double pipe heat exchangers, multiple such tubes are arranged in a common shell, then it is called as a shell and tube heat exchanger. So we will look at that later on. Okay. So let us concentrate on our analysis which we have done earlier for a flat slab here. This is the flat slab we have used. Now we are having a concentric pipe. Okay. So for this, how our temperature and water excess are going to look at. So here inside this pipe, there is a temperature which is Ti. So Ti is the bulk temperature of the fluid, isn't it? Twi is nothing but the surface temperature here at the inner wall. Hi is nothing but the heat transfer coefficient for the inner fluid. Similarly, the outer surface temperature of this pipe, inner pipe, is going to be Tw naught. And T naught is nothing but the bulk temperature of the annular fluid. H naught is nothing but the heat transfer coefficient for the outer fluid. Ri is the inside radius of this pipe, inner pipe, and R naught is the outer radius of this inner pipe. Do you all able to see what I'm trying to say here? Is the problem clear to everyone? Is the system is clear to everyone? Hello?
Yes.
No, sir. Could you explain it again, please? The diagram at least.
Good. Thank you. Okay. This is what the instrument we are looking at. So there are two concentric pipes. So this is the outer pipe. This is the inner pipe. Now what I'm saying is one fluid is flowing through this inner pipe like this. One fluid is flowing through this inner pipe. Let's say this inner fluid which is flowing through inner pipe is at a higher temperature, let's say. Similarly, it could be at a lower temperature also, doesn't matter. And there is another fluid which is flowing through this annular region outside this inner pipe, this annular region. So that fluid is moving here in the annular region and going out again from the annular region. Is it clear? Yes or no?
Sir, so the fluid in the annular region is moving in the circular fashion.
The fluid in the annular region will be moving around this pipe.
Yes,
around
sir, yes.
This pipe. Okay. So this is the inner pipe. This fluid in the annular region will be in this entire annular region here.
Yes,
is it clear? So
yes,
second fluid is flowing through this annular region here, entire thing. And the another fluid which is there, which is flowing through this inside pipe. Okay. So both annular fluid and inside fluid are separated by this metal wall. Do you all agree?
Yes, sir.
Now, both the fluids are moving. One fluid is moving through the annular region, another fluid is moving through the inside pipe, and therefore there will be a heat transfer coefficient inside as well as outside. Do you agree?
Yes, sir.
So there is a heat transfer coefficient here outside in the annular fluid. Similarly, there will be heat transfer coefficient here inside in this fluid, isn't it? So this heat transfer coefficient is Hi. Here the heat transfer coefficient is H naught, isn't it? Now temperature, bulk temperature of the inside fluid is Ti. Bulk temperature of the annular fluid is T naught, isn't it? Again, on this metal wall, which is a cylindrical metal wall, this cylindrical metal wall inside surface temperature is Tw1 and outside surface temperature is Tw0. Is it clear?
Yes, sir.
Okay, now we are looking at this entire system. So same argument we are making again, the same argument which we have made earlier. That argument was the heat transfer between this inside fluid and this metal wall is going to take place by convection, isn't it? Do you all agree?
Yes, sir.
Because this fluid is moving, isn't it? So the heat transfer by this fluid to this metal wall will be by convection. So that we can obtain by using a Newton's law of cooling. So that is given as Q is given as HI AI delta T, isn't it? Correct. Where HI is the heat transfer coefficient inside here. AI is the heat transfer area. This heat transfer area. This heat transfer area AI into delta T. And what is delta T? Ti minus TWI. Ti is the bulk temperature and TWI is the surface inside surface temperature here. Do you all agree?
Yes, sir.
The only thing you need to look at carefully is here this heat transfer area is going to be AI, which is this surface. Remember, heat transfer is going to take place on this metal surface here, inside metal surface here, isn't it? Do you agree?
Yes, sir.
So again, we can rearrange this. We can get Ti minus TWI. That is given as Q divided by HI AI. Yes or no?
Yes, sir.
Now let's concentrate on this metal wall, this cylindrical metal wall here, isn't it? This metal wall, since in this metal wall the heat transfer will take place by what? Conduction. And for cylindrical metal wall, the conduction equation we have already derived, isn't it? In the conduction itself we have derived, and this is what the equation which we have obtained there, isn't it? So Q is given by 2 pi L Kw TWI minus TW2 divided by ln R0 by Ri. This equation we have already derived earlier, isn't it? Do you all agree? For
Yes.
a cylindrical wall, again we can rearrange this equation. We can get TWI minus TWO, and that is given as Q ln R0 by Ri divided by 2 pi K KWL, isn't it? Similarly, now let's look at outside of this metal wall. Outside of this metal wall, heat transfer will be by convection again. So that is again given as Q is given as H0 A0 TW0 minus T0. Here TW0 is nothing but the wall temperature here, minus T0. T0 is the bulk temperature of the annular fluid. H0 is the heat transfer coefficient outside, and A0 is the outer surface, going to be the outer surface of this metal wall. Do you all agree?
Yes, sir.
So we can rearrange this and we can obtain this temperature difference as TW0 minus T0, that is given as Q divided by H0 by A0. Correct. And since I said that this surface temperature, finding the surface temperatures is very difficult. So we always represent our balance equation or heat transfer in terms of known temperatures which can be calculated easily. And calculating the bulk temperature is easy, isn't it? So we can add all these temperatures. By doing that, we can represent this entire temperature difference in terms of the bulk temperature of inner fluid and bulk temperature of the outer fluid. So Ti minus T0, isn't it? So Ti minus T0 is given as Q. We can take common here, and what we will get here inside the bracket is 1 upon Hi Ai plus 1 upon 2 pi L Kw divided by ln R0 by Ri plus 1 upon H0 A0. Correct, isn't it? Again, one more thing to note down, that we are not looking at unsteady state. We are not looking at generation term, that therefore this capital Q will be same. Capital Q here in this metal wall, outside, everywhere it is going to be same. Do you all agree?
Yes, sir.
So we have taken Q common. We can rearrange this equation. So we get Ti minus T0 divided by this entire thing, isn't it? Correct? Yes or no? Now it is customary. It is, see, remember earlier case also how we have represented this Q. Whenever we have a conduction and convection combined, we represent our equation in terms of overall heat transfer coefficient. Now in this case, the problem is this overall heat transfer coefficient can be represented in terms of inside surface area or outside surface area, isn't it? Because we can have, see, unlike the previous case, here this surface area and this surface area, both the surface areas were same cross-sectional area. But in cylindrical geometry, my inside surface area AI and my outside surface area both are different. It's not same. So that means this U, overall heat transfer coefficient, I need to define in terms of inside surface area as well as outside surface area. Okay, so if we represent this U in terms of outside surface area, in that case, this equation Q is going to become what? U0 A0 delta T. So general form is what? U into A into delta T, isn't it? Now, if you define U as U naught, then the area should be again A naught. Do you all agree?
Yes, sir.
And if we define this U as a inside overall heat transfer coefficient in terms of inside surface area, then it is going to be UIAI. So it depends how you are defining U, whether it is with respect to outside surface area or with respect to inside surface area. And note down that U naught A naught is same as UIAI. This delta T is same. So now this denominator, remember this denominator we have represented in terms of U. So this denominator now we are representing in terms of U naught as well as UI. So in terms of U naught, what we will need to do, we have to multiply this here by A naught. Then and then only we can multiply this U naught A naught, isn't it? So 1 by U naught will be given as A naught by HI AI plus A naught ln R naught by Ri 2 pi LKW plus 1 upon H naught, because A naught get cancel out, so that will be 1 upon H naught. Again, AI by A naught here will be what? This is okay. So what will be the surface area here? Inside surface area? Pi dl. Remember, the heat transfer is taking place over this surface or the length, isn't it? It's not only at this instant here at R. This is over the pipe, isn't it? If I go back here, this will be the inside surface area, isn't it? This entire thing. So what will be this circumferential area? Pi dl, isn't it? Similarly, outside surface area pi d naught l, isn't it? Inside surface area will be pi dil. Outside surface area will be pi d naught l, isn't it? So that means this AI by A naught will be A naught by AI will be represented by what? D naught by Di or R naught by Ri. Do you all agree? Is it clear or not clear?
Yes, sir. Yes, sir.
Yes, sir.
So similarly, if we represent this overall heat transfer coefficient with respect to the inside surface area, what we get is 1 by UI. 1 by UI is given as 1 upon HI, because here AI by AI will get cancelled out. And here we will have AI ln R naught by Ri divided by 2 pi LKW plus AI by A naught HI. And again, this AI by A naught we can replace by Ri by R naught. Ri by R naught. Okay. And this AI again will be what? Pi DIL, where L is the length of the pipe, Di will be the inner diameter of this pipe, and L will be the length of the pipe. Is it clear to everyone? Can you see the difference with respect to the flat geometry and the cylindrical geometry? In the cylindrical geometry, this overall heat transfer coefficient also need to be defined in terms of the inside surface area or outside surface area, and depending on whether you are defining it inside surface area or outside surface area, you will be multiplying that corresponding area in this equation. So if I define U in terms of U A naught, then I will be multiplying A naught in this equation. Otherwise, if I define this U in terms of inside surface area as UI, then I will be multiplying AI here in this equation. Okay, so let's look at one example and conclude today's class. So a stainless steel rod of outer diameter 1 centimeter, originally at a temperature of a stainless steel rod of outer diameter is 1 centimeter is given at a temperature of 320 degrees Celsius, is suddenly immersed in a liquid of 120 degrees Celsius, for which the convective heat transfer coefficient is 100 watt per meter square Kelvin. Determine the time required for rod to reach the temperature of 200 degrees Celsius. For stainless steel, rho is 7800, Cp is 460, K is 40 watt per meter Kelvin. Okay, so this is again an unsteady state heat transfer, but we will see, can we simplify this using this lumped capacity assumption or not? Okay. So in this case, again, take for a simplicity, let us assume that the length of the wire is 1 meter. Okay, so calculate the volume. volume will be pi by 4 d square L, isn't it? So L we already know 1, D is given 1 centimeter. So we can find out the volume. Similarly, area will be pi dl. So pi dl is because the heat transfer is going to takes place over this entire area, isn't it? So pi dl will be 3.14 into D is 0.01 into 1 meter length. So we have obtained this. What will be characteristic dimension here? Remember, we need to calculate a Biot number here, because if you wanted to apply a lumped capacity method here, then we need to find out the characteristic dimension. So characteristic dimension will be volume divided by area, isn't it? Volume divided by area. So if I divide this volume by area, what I'm going to get is D by 4. That is what the characteristic dimension I am going to get. And what will be the Biot number?
Sir, why
HLC?
have we divided volume by area? I did not understand.
Because we are not using a spherical surface here. It's a cylindrical surface, isn't it? So characteristic dimension you calculate by you represent this entire why we obtain the characteristic dimension is because all these equations we derive based on the spherical surface, and when we wanted to apply the same concept to the cylindrical diameter, then we represent it in the equivalent form. So equivalent form will be based on the characteristic dimension. So characteristic dimension in this case will be volume by area. Okay, the same thing you might have studied in fluid mechanics, if I'm not wrong, is it? If you apply the concept of fluid past the non-spherical surfaces, so how you calculate the equivalent diameter there? Remember, for calculating the drag force, etc., you require to calculate the diameter, isn't it? And there you assume that the entire particle is a spherical, but very often you do not have a spherical particle, isn't it? So how you represent non-spherical particles? By using a equivalent diameter, isn't it? Yes or no?
Yes.
So this characteristic length is similar. Is it clear to everyone?
So for a sphere, will we take characteristic or R by 3 V by A?
So see, in case of flat thing, it will be just L, but there in case of that is I think R by 3, if I'm not wrong.
For a sphere.
I think characteristic dimension.
So for all the shapes we have to do V by A only for finding the characteristic.
Correct.
Okay.
For characteristic dimension, correct.
Okay.
So in this case, that will be D by 4. So again, so this characteristic dimension is required because here we need to calculate Biot number. Okay, and Biot number we wanted to calculate by using this formula HLC by K. Remember, that is what we have used HS by K, where S we have assumed as a characteristic dimension. I have just changed the notation that S to LC here. Other than that, it is everything is same. Is it okay?
Yes, sir.
So if you calculate this Biot number, so in the Biot number, this K has to be thermal conductivity of the metal itself, isn't it? Correct?
Yes, sir.
So we put this K equals to 40 here. We calculate 6 into 2. We get this 6.25 into 10 raised to power minus 3. And definitely this is much lower than 0.1. Yes or no? So with this, what we can assume? We can assume that the internal resistance for heat conduction inside the metal rod is negligible. That means the entire metal rod is more or less at a same temperature. Do you all agree?
Yes, sir.
Yes.
That's what we are, concluding by obtaining this Biot number. Remember, in previous case, another problem which we have solved. In this problem, why we have not calculated the Biot number? If I ask this question, why we are not calculating the Biot number? Because here we are not looking at the conduction inside. Remember, because the temperature of this ice ball was anyway remaining at the constant value because of phase change. Correct? Isn't it? That's why we have not obtained the Biot number here. It is not required at all. But in this case, we are also looking at the conduction In this case, we are saying that whether the conduction will be there or not inside the metal. Here we are looking at the metal rod, isn't it? That's why we are calculating the Biot number. Is it clear to everyone? Yes or no? Because what this Biot number is going to give me the information. It is going to give me the information that whether my metal rod is going to be at uniform temperature or not at any given time instant. That is what we are calculating. In the earlier case, it was already there at the zero temperature at any time instant, because it was a phase change was taking place there. Yes or no? So that's why we have not calculated a Biot number there. And anyway, the conduction was not taking place. It is only the outer layer was getting melted, isn't it? So there is no conduction inside the ice ball was taking place there in the previous case. But here the conduction inside the metal is going to be there, and whether that conduction is going to be whether that conduction resistance is going to be dominating or not, that we are calculating based on this with respect to the convection. Yes or no? Does it make sense what I'm saying? Please say something. Hello?
Yes, sir.
Confidence was lacking.
So in the ice ball, we assume that the whole ice ball is at 0 degrees Celsius, not in the negative. No?
Because it's a ice present at a zero temperature, isn't it? So we are assuming that that temperature is not going to change and we have assumed that the sensible heat is not there. Okay, so whatever the heat is added only is going to reduce the size of the ice ball, but the temperature of the ice ball is not going to change. Okay, so there is no conduction taking place inside the ice ball.
Sir, if it would have been an ice ball at a temperature less than 0 degrees Celsius, then we would have considered lumped heat.
Then we would have considered. Yes. You are absolutely true in that. Correct. Then we would have considered that.
Okay, sir.
But in this case, the conduction is also taking place inside. Here the conduction is also taking place inside, but the only thing what we are looking at, what this Biot number is. This Biot number is going to give me whether the conduction resistance is dominating or not dominating. Can we neglect this conduction resistance with respect to the convective resistance which is present outside? And when the Biot number is less than 0.1, very less than 0.1, then what we are saying that whatever the change in the surface temperature is going to be there on the metal wall, that would be immediately will be affecting the entire metal rod, instead of taking some time to it is not going to take some time so that that temperature gradient will be there. No, it will be immediately, that will be spread across the rod. So time, if you look at the order of magnitude for time in conduction and the order of magnitude of time in convection will be very different. Conduction is going to occur very fast compared to the convection. That is why the conduction resistance inside the metal rod we are neglecting. Do you agree? Remember the Fourier number we have said? That is what that it was comparing that time steps. Is it clear? Is it clear? Yes or no? We will get a similar expression here also. All right. So then this is the same balance equation which we have seen earlier, isn't it? Heat lost by the body is equal to the decrease in the internal energy of the solid. So rho v Cp dt by dt, that is the heat lost by the change in the internal energy, and that should be equal to the heat lost by the body. Heat lost by the body will be given by HA delta T, isn't it? Correct? Yes or no? Actually, this minus sign is here. It should be here. So temperature of the rod is decreasing with respect to time. So this minus sign I have taken on the other side. Okay. Is it clear?
Yes, sir.
So we can rearrange. Hello. So after integrating, what we get is ln T minus T naught is given as minus HA rho CV rho CPV T. This is the same equation which we have obtained earlier, isn't it? So this is nothing but the multiplication of Biot number into Fourier number. Yes or no?
Yes, sir.
Plus C1, and then we can apply the initial conditions. So at boundary conditions are at t equals to ti, t equals to small t, time equals to 0, t equals to temperature, t equals to ti at time equals to 0. So C1 will be given as ln t minus ti minus t naught, ti minus t naught should be equals to minus ha rho v cpt. We can rearrange this. So after rearranging t minus t naught divided by ti minus t naught is given as exponential of minus ha divided by rho v cpt. This equation we have already derived earlier. I can put all the values here. So initial temperature is okay. So the current temperature is 200 degrees Celsius. Okay. Temperature of the bath is 120. Initial temperature is this 320 minus 120. And we can calculate the time by putting all the values here. So time comes around 82.18 seconds. Is it clear to everyone? Hello?
Yes, sir.
All right. So we stop here unless you have any question, anything you wanted to ask me. Is it clear to everyone? So we will be having a tutorial on Saturday. Is it? Saturday is working?
Yes.
Yes, sir. Yes, sir.
I was waiting for a tutorial on 26 January. I thought people will come, but nobody. I think one student came but all right. Anyway, we will have it on Saturday. Okay.
Sir, you told that you will tell about the quiz also.
So, okay. So can we have a quiz before the minor or can we have it later? It doesn't matter because quiz and minor both are going to have a same weightage. Doesn't matter.
Are we going to have only
Before-
one quiz?
No. So one minor and 2 quizzes. So total 3 and base 2 we will consider out of these 3, isn't it?
Sir, before the minor. Before the minor, sir.
Yes, sir.
Before the minor. So minor is from 30th, is it?
So 14th of Feb.
14th of Feb. But the only problem is I wanted to have some material covered, isn't it? So I wanted to space them equally so that, you know, so that some more material will be there, isn't it? So if we have a quiz, let's say next week, then the same syllabus will be almost there for both quiz and minor, isn't it? That's not good, right?
So you can take later also.
So we will have it after the minor. But as I said, no question, nothing is going to get repeated. Also, what I wanted to say clearly to you is quizzes and minors will be proctored. So you will have to switch on your videos on Teams. I'm going to make 7-8 teams and several, you know, students, my students, as well as I will ask some faculties to help me to conduct this online. So any of you, if you switch off your video in between, then you will be considered as absent. So you will all have to write the examination in front of us. So that is why please do not rely on your friends for getting the pass grade. Please, try to believe in your own abilities. Okay, you all are able, and I am damn sure that you all can, you know, do well. Okay, so believe in your abilities rather than believing in doing some, you know, unfair means. Okay, that's what I'm requesting all of you. Can we stop here unless you have any question?
Yes,